All right. Okay. Hope all of you had a good break and are ready for the second half of the semester. Is it roughly half, or I don't know how much is left? So we'll recall that we're doing graphs, just in case you've forgotten that. So we're going to do shortest paths, and we know that breadth first search gives us shortest paths in unweighted graphs. What does unweighted graphs mean? That every edge has weight 1, basically. Right? That's, we think of it as unweighted, right? And typically breadth first search is explained as a search strategy with a Q data structure. I think it's better to think of it as exploring the graph in increasing order of distance from a given source vertex, right? So to make that concrete, you can think of an alternative algorithm which is based on layers or an increasing order of distance from the source. And it starts off with saying that, okay, S is at distance 0 from itself, right? So the layer 0 is a set of all vertices at distance 0 from the source, and that's S itself, right? There's nobody else, at least in the unweighted case. And then we try to find vertices of distance 1 from S, which is the layer 1, and that we know how to do, right? What is layer 1 is a set of all vertices at distance 1 from the source. That's simply the vertices adjacent to S, right? But what is at distance 2 from S? Those are vertices which have a path of shortest path of length exactly length 2 from source, right? So we can define it inductively as the neighbors of vertices at distance 1 who are not already in layers 0 and 1, right? That's one way of defining it, right? So we can build up these layers inductively, right? And that's what this algorithm is doing, right? Initially the layer is 0, you start with S, and while there are vertices at distance in Li, that is, we already found layers L0 to Li, and we want to find Li plus 1, we look at all the neighbors of vertices in Li which have not already been discovered, and those are precisely the ones in layer Li plus 1, right? So for each vertex in layer Li, look at all its neighbors. If anybody is not already visited, that means we've discovered a new vertex which is in layer Li plus 1, and we add it to the layer Li plus 1, okay? And that's really a very simple algorithm. It's explicitly making this notion of discovering vertices in increasing order of distance rather than saying it's in a queue or something like that, right? So, and it's easy to check that this can be implemented in linear time. And just so that we have a rough idea, so we start out with, say, we want to explore the graph from which vertex? 4, okay, right? So L0 is 4, and so we start out with 4. We create a tree as we go along. And what is L1? We take out somebody from L0 and explore all its neighbors. And what do we get? 2 and 5. We create edges because we are discovering them for the first time. And when we discover them, we add them to L1 is 2 and 5, right? And now we want to discover L2. We pull out each vertex in L1 and explore them, right? And we say, okay, we pull out any order, we don't care. Pull out 2. Well, we'll find an edge to 5. Okay, that's it's already discovered, so it's an intralayer edge. And what else do we discover? 1 and 1 and 3. So we also create this layer L2. We say, okay, 1 and 3 and 5. Find something which has already been discovered, and 5 discovers one more at layer and 6, right? Okay, 1, 3, 6. That is layer L2. And now we discover, we are done with layer L1 because we explored 2 and 5. Now we explore L2, 1, 3 and 6 and pull them out. And 1 doesn't discover anything new, right? And it may discover this edge. And 3 discovers 7 and 8. Okay. And we create L3 as 7, 8 and whatever else, 6 doesn't discover anything else, and so that's it. And then we pull out L3 and we discover, we don't find anything else and we are done. Yeah? It's simple enough, right? So what is the important property that these layers have? Well, first the layer I is precisely the vertices at distance I from the source, and because of it's an undirected graph, any non-tree edge can only be inside a layer or to a layer which is adjacent to that layer, right? You can't, if you look at the dotted edges can't jump across layers because that will violate the shortest path property, yeah? So the structure of the BFS exploration gives us something which is different from what DFS would do, right? And it has its own uses, right? Structural uses, distance computations, of course, are the most important thing here, but for example, you can discover whether a graph is bipartite and find if there's a graph has an odd length cycle using BFS. You can read about that in the notes, okay? Okay, so that's the property in undirected graphs, and the directed graph setting is a little different, right? As always, you have to be a little careful. Again, you know, you will discover, you know, if you start it from, say, what vertex do you want to start from? F? Okay. So F is layer 0, right? And then it discovers B, and what else does it discover? B. Okay, so that is layer L1, B and G, and then we pull out layer, if we take out B, we get E, L2 is going to be E, and anything else? No. What about G? Oh, okay, G doesn't discover anything, right? So L2 is just E, and then E, you pull out E and E discovers H. Okay. Okay. Okay, so one thing we need to realize that, you know, you can have an edge like this, right? And in this case, maybe H has an edge to G, right? Yeah, okay. Okay, so inductively you can again prove that the layers give you vertices in increasing order of distance from the source vertex, right? But one important property which is a little different than in undirected graphs is that you can see that we have an edge from H back to G which is jumping a layer, right? Yeah? Make sense? So this is layer 2 and we skipped. So backward edges in directed graph can jump layers, but forward edges cannot jump layers, right? Does that make sense? You can't have an edge from G to H going this way because that would violate the distance problem. Yeah? Okay, that's difference from a directed graph and undirected graph. Okay, so that's the property. So now we want to make the problem more interesting, right? We have lengths on the edges, right? And that gives us a shortest path problem. So you have a graph, a source vertex, you have lengths on the edges, and for now we'll assume that the lengths are not negative, right? We'll come to the situation where the lengths can be negative in a little while, right? So we just want to have lengths on the edges, and what are some canonical problems? Given a source and a destination, I want to find the shortest path from S to the destination, right? Remember, the more basic problem is there a path from S to T, right? That's a reachability problem. Here I want among all, if T is reachable from S, I want to find the shortest path among all those paths, right? It's an optimization problem. And the next more general problem is, like with reachability, find the shortest path from S to everybody, right? And not just one vertex. And the more general problem is, for every pair of vertices, find the shortest path, right? It's a reachability for all pairs with shortest path, right? Many applications because usually you want to find a path which has some nice properties, not just any path, right? So of course now it's easy to explain to people, by using maps. It's easy to explain what maybe goes on in an algorithms class, right? How do you find the shortest path distances in maps and stuff? Okay, first we'll assume the edge lengths are non-negative, right? And then we'll come to the negative, right? Okay. So we'll restrict attention to directed graphs for simplicity, not that, right, because we don't want to cover both directed and undirected all the time. We can reduce the undirected graph problem to the directed graph problem. How? How do you reduce shortest path problem in undirected graphs to the directed graph problem? Yeah, take an edge, and I don't want to think of it as splitting, because I want to think of it as replacing it with two edges, one in each direction, right? And this reduction works. You have to verify to yourself that, shortest paths in undirected graphs, if I take a graph G which is undirected and replace that with a directed graph with two edges in both directions for each undirected edge, that shortest path distances are fine as long as, this is an important caveat, the edge lengths are non-negative. We'll see that it doesn't work if the edge lengths are negative, okay? We'll come back to that, right? You always have to think about why it is not the case, yeah. Edge length can be 0, yes. Yeah, edge length can be 0, yeah? That's okay, yeah? Nothing stopping us from edge lengths having 0. Less than 0 is a different issue. That creates some subtlety, right? Okay, edge lengths can be 0, yeah? Okay, so that's, it relies on non-negativity. You should figure out why it relies on non-negativity. Okay, so, let's first understand, right? If all the edge lengths are 1, what algorithm would you use? BFS, right? Yeah, because we already saw that's what it does, right? Okay, so we know how to solve the problem in a very interesting special case, which is perhaps more common than the case with edge length. Okay, so now so we know we have a very simple algorithm for a special case. So what about the more general case, right? Moreover, you know that it's actually a very efficient algorithm. It's a linear time algorithm. Okay, suppose, I told you that the edge lengths are all integers, and you want conceptually to understand the problem, what would you do? Suppose I tell you that all the edge lengths are between 1 and 10. Sorry? Yeah, right, edge length between, it's an integer, if I have edge length 5, I'll split it into an edge of length 5 into 5 edges, right? I put vertices in the middle, yeah? Okay? So you can do that. Nothing stopping you from doing that, right? So if I have an edge which looks like this, 5, I can do this, right? Let me direct it for simplicity. Okay? So, and I'll say, okay, now I'll pretend this is U and this is V. I created extra vertices, and all these are of length 1, right? Problem solved, right? Okay? But it's a very important observation, and it's not particularly important that is, integers, they're rationals, you can do things, right? But the important thing you need to realize is that we already know how to solve shortest path problem even if the edge lengths are not 1, conceptually, okay? BFS will do it for us, right? What is the only problem with doing this? Sorry? Yeah, so we change the graph into much bigger graph potentially, right? That's the problem with this, right? Nothing wrong with it. Actually, this is a very efficient solution if for some reason that in your graph that the edge lengths are always between 1 and 10. Not a big deal, right? Conceptually, it's actually a very simple solution, okay? The only catch is efficiency, right? If you have an integer with, if the edge is of length 10,000, you're in trouble, right? You have to put 10,000 new vertices, right, for every edge. That's slow, right? So the problem with this reduction is only that it's inefficient, not that conceptually it is not the right thing to do, right? Okay, so so why does BFS work? So now we say, okay, so the idea for Dijkstra's algorithm is nothing but the following, right? See, we know how to use BFS to solve shortest path problems if all the edge lengths are 1, okay? And we know, let's assume all lengths are integers. We can reduce the general problem to BFS, right, by using this trick, right? Okay, the only catch is seems silly because if you have 100 length, we are putting 100 vertices, it's making the graph big, right? The idea of Dijkstra's algorithm is really, can we simulate breadth first search in this implicit graph without actually creating the graph, right? Does it make sense? We know breadth first search will work, but can we not actually split the graph and do all this extra thing and implicitly do it, right? Or another way of saying it is, well, what made breadth first search work? Why can't we just apply the same principle when we have edge lengths, okay? But we don't want to split the graph and actually keep track of all the new vertices, okay? All right? So that, I mean, you can think of it two ways: implicitly running breadth first search on this graph without actually creating the graph, or what made breadth first search work? Let's go with the same principle, okay? All right, and either way is fine, right? So the main thing that you should get from breadth first search is that we can explore the graph in increasing order of distance because shortest path distances have a nice property, right? What is that property? It's very simple. Suppose, we have a shortest path S from V0 to Vk, right? What can we tell about anybody in the middle of that path? So I tell you that this is the shortest path. V0 to Vk is the shortest path. Then I claim for anybody in the middle, this prefix of the path must be a shortest path to that vertex, right? It seems obvious, right? Yeah, and it is obvious, right? How can it not be the shortest path to that middle vertex? Because if I have an alternate path, I should take the alternate path, right? So you claim that this is a shortest path from S to V6, and for anybody in the middle, if say V4, if this is not a shortest path from S to V4 and there's an alternate path, then to V6 I should take that path, right? Why would I take this path? This should not be the shortest path, right? So it's a completely obvious property, no? Okay, but there's one catch though. It's a very simple property. If the edge lengths, this property doesn't depend on the edge lengths being negative or non-negative. Okay, I did not use the fact that anywhere that the edge lengths are negative or non-negative, right? Okay, but one extra property we get if the edge lengths are non-negative is that not only is this shortest path from S to V4, the length of this path must be less than the length of S to V6. Yeah? Why? Because all the edge lengths are non-negative, right? But if the lengths are negative, that property is not true, no? Okay? Okay. But what does it mean? Just like breadth first search, if I have a shortest path to a vertex, everybody on my path who comes before me should have actually shorter distance to the source, right? So we can explore the graph in increasing order of distance from the source. Because, to get to a vertex, I have to get to people who are before me in terms of distance, right? So the idea is just the same as breadth first search. Right? What are we doing in breadth first search? We first find everybody at distance up to I, and then we increase the distance to I plus 1, right? That relies on the fact that to get to I plus 1, you have to go through vertices of distance I, right? So we can inductively build that same structure, and that's really what Dijkstra's algorithm is, right? what is the algorithm? You say, okay, who is the shortest distance to S itself, right? Who is the first guy? Sort everybody in increasing order of distance. Can we find the next guy? Okay, the guy with the distance which is closest to S, okay, and then the next guy, because we know that we don't need anybody else to reach the ith guy. We only need to go through the first I minus 1 guys, right? We don't need to go through the guys who are after him. Okay, so that is the basic idea of Dijkstra's algorithm, right? You start with S, and then you say the invariant you maintain is you have already found the I minus 1 closest nodes to S, and then among the nodes which you have not already found a distance to, you find the one who is next in the distance order. Okay, how do we find that? We'll figure that out, right? And we keep doing this in a loop. Okay, that makes sense? Yeah. Okay. Okay. So how can we implement this this next guy? Let's see, right? Let's do it by an example. Okay. So suppose this is the graph which has lengths now, non-negative lengths. So this is the source. Well, we know its distance to itself. This is the first guy, right? Who is the next guy? The next guy must be adjacent to this guy, right? All right. Okay. Is it this guy, this guy, this guy? This guy, right? Why? Sorry? The shortest length. So why? I mean, let's think formally. What's the proof, right? That this guy is the next guy. Okay. Okay, it's one of these three. Can it be this guy? Well, it's this path has length 9, right? Okay. Oh, it can't use that path because that path would be of length 9, right? Maybe there is a path which goes around and comes to that guy which is length less than 6, right? Is that possible? Not possible, right? Because lengths are non-negative. Okay. Yeah. You will see that it's not true if the lengths are negative, right? It's non-lengths. Okay. Okay, so we know the next guy is going to be 6. Okay, that was easy, right? That was not hard. But what is the second guy? Who is next closest to S? Okay, why? Right? Let's again ask you, why is it B? And now we have to be a little bit careful, right? Maybe we know again that the next closest to S, the source, would be somebody who's adjacent to this guy or this guy, right? Yeah? Okay. But we should consider nodes adjacent to C as well, right? Yeah? We should look, maybe this guy would be, is it, so how do we evaluate? Okay? How do we evaluate, whether this guy is maybe has a shorter path? So we think it is 9, right? But if this guy was 1, what would you say? You would say this guy, right? Okay. So how did you figure that out? What calculations do we need to do, right? Okay. So we'll continue, right? We figured it is 9. So what is the next guy? Now things are getting a little bit harder, it seems, right? Who is the next guy? G, E. Okay, why, right? You say, okay, 6 plus, you say, okay, 13 is smaller than what, right? Okay, so what are we doing? How do we figure that out? Okay, so we say, okay, who are the candidates, right? That could be the next guy. Okay, this guy, this guy, this guy, because they are all the ones adjacent to this. Okay, among these, how do we evaluate? Sorry? So we say, okay, what is the shortest path from the source to this guy using these 3 guys, right? Right? Let's calculate that. Can we calculate that distance easily? How? What is the shortest path to D using only these 3? Well, we know the shortest path distance to this guy and the source already, right? Inductively, we found the right distance to them. So the distance to this guy using only these three is what? The path could come to D from any of them, no? Yeah, we only have to worry about the last leg of that path, no? So we say, aha, if you came through 6, the distance would be whatever is the shortest path to C, which you already know is 6 plus 30, that will be 36, right? There is no other way to reach this guy from B or A, so well, there's only one way to reach D using these three vertices, so there is no way it can come with less than 36. Yeah? Sorry? Consider what? D? Oh, that's because I'm only interested in finding distances through the explored nodes, not the unexplored nodes. Okay? All right? Okay, how can I reach F using only these three nodes? Well, I can come through two ways, right? Yeah. So I can go this way. What would that give me? 6 plus 18. If I go this way, I'll get 9 plus 18, which is shorter. 9 plus 18, right? I can't get through A directly, so the shortest path distance from A to F using only these three nodes is what? 19. To this guy is what? 36. And what about this guy? 13. Which is better? Okay, I want to claim that that is the next shortest guy. Why? Okay, that's what we need to understand. Okay, so what are we doing? We already explored the first I minus 1 guys, right? And then we are finding the distance to everybody else using only these I minus 1 guys. Okay? Okay? What did we find? For this guy it's 19, for this guy it is 36, and this guy is what? Okay. What property do these distances satisfy? They must be at least as much as the shortest path distance, right? Yeah, they cannot be less than the shortest path distance, right? Because we are restricting the set of paths. I'm not allowing you to use all the possible paths, right? I'm only allowing you to use these three guys. So every number I calculated for everybody is at least bigger than the shortest path distance from the source to that vertex. Yeah? Great. We get a number which is bigger than the shortest path distance because it's some specific paths I'm allowing you to use, right? But this guy is precisely the guy who will be the next guy because we know the next guy doesn't, the ith guy doesn't need anything other than the first I minus 1 guys. Yeah? Okay. So that is the, I want to claim that this guy is the 1, 2, 3, fourth guy in order from the source. For this guy, the estimate must be correct. Okay. Okay, so let's do the algorithm and then if we don't worry about the proof right now. So we found the first 4 guys. What is the next guy we should figure out? Okay. For everybody, calculate what is the shortest path to that guy using only these 4 vertices. Yeah? What is the shortest path to F now? The same thing, right? It didn't change, right? Did it change? No, because this guy didn't have an edge to that, so that doesn't change, right? So what about this guy though? Well, maybe it is 13 plus 20, yeah? Previously it was 6 plus 30, right? 36, but now it is what? 33. So this guy's distance changed because we had one more guy in this list, right? So what about this guy? It is 13 plus 25, which is still, right? So among these three, these are the only 2 candidates, these are the 3 candidates now, right? I also have, this is also a candidate except that it's infinity, right? Because with just using 4 guys, I can't get to that guy. So you might as well call it infinite, right? So among these 3 guys, who has the shortest distance using only these 3 guys, the 4 guys? I guess it is F, right? Yeah? So that guy is the next guy I claim, right? Okay? And then we update because now this guy's distance changes. Now it's 19 plus 6, right? So we update. This guy has a shorter path and so it becomes next and so on. Okay? All right. So is the algorithm clear? Right. What are we doing? We are inductively finding the next guy in the order if we are sorted, right? If we sort that, who's the next guy, right? Why is the algorithm is simple, right? What is the algorithm? You start with the source, okay? And we want to find the next guy. So at every step, we are finding a distance to every vertex who is not yet found using only the things we have already found, right? We can't, so in the first step, we only know the distance to the source, so we're increasing a ball from the source, right? We're trying to find, if I increase a ball of radius r, who will I hit next, right? Who's the first guy I'll hit, right? Okay, well, it turns out that, it will be 6, because from the source, you can only use one edge, then C is the first guy you'll hit, right? Okay, now we're increasing the ball some more, who will we hit? Okay, now to calculate that in a graph setting, because we are not in a continuous space, we look at everybody and say, what is the distance to this guy if I only use these two? That I can easily calculate, right? I look at my edges coming into me, and I say, okay, I'm getting an edge only from this guy, so my distance using only these two must be 6 plus 18, right? Just using those two, we calculate the distances, and among all of them, pick the one which has the lowest value. And I claim that guy must be the right guy who is the the third smallest. And that turns out to be this guy, and again we do the calculations, again we find the one which is smallest, that will be the next guy, and so on. Yeah? All right? Is the algorithm clear? Yeah? Okay, so now, why does this work? Here is I claim we are just doing breadth first search, okay? We're doing it implicitly. If in fact you did the splitting of the edges, what will happen? This guy will have 6 vertices, right? Yeah, this guy will have 9 vertices, right? So you're kind of growing a ball implicitly, right? Where, you'll be somewhere in halfway on the edge, right? Yeah, that's what BFS will do. If you actually split the edge, BFS will go halfway into the edge and stay there, right? But we don't want to keep track of all that, right? Yeah. This is Dijkstra's algorithm. Yeah, right. This is Dijkstra's algorithm, right? Okay. So it is nothing but the following principle, right? You already found the I minus 1 closest vertices to a source. You want to find the ith guy, and this is how you maintain that information. Okay. So how do you find the ith guy? Okay. Here is the thing, right? Okay. But every vertex which you already have not already found, define this distance d prime su to be the shortest path length from S to U using only the first I minus 1 guys. That means you cannot use anything else in that path. Okay? Okay? Is the definition clear? Okay. First observation, the real distance from the source to U must be less than or equal to d prime su. Why? I'm not allowing you to use all possible paths. I'm only allowing you to use the first I minus 1 guys. So clearly my distance has to only increase, no, if I restrict you, right? Yeah? Okay. How do you calculate this distance? How do you calculate d prime su? What is d prime su again? The distance from S to U only using the first I minus 1 guys, right? How can I calculate that? I claim it is, look at all the vertices that I already found the distance to, take that distance S to T plus the length of the edge from T to U and minimize this over all T. Yeah? So in terms of the example, if I already found the distance to these guys, I want to find the distance to D or F using only these 4 vertices. How do I find it? I look at how can I get to F. I can get to F using this edge or that edge, right? If you get to this edge, then it must be this distance plus that distance, right? So it is 6 plus 18. Okay, okay, so a little bit careful. Now, what about the distance to D using only these guys? I look at all the edges coming to this. right? If I come through this, I don't care how long the path is, I already know the right distance to this guy, right? So it is 6 plus 30 this way, 19 plus 6 this way, 13 plus 20 this way. I take the minimum of all those things. That's the right distance, no? Okay, so I know how to calculate it, right? How do I calculate it? Very simple. So this is what I can calculate, right? Okay. Then the claim is, if you look at all these d prime values and take the minimum of them, that guy is surely the ith guy. Okay? That we found the right distance to that guy. Okay? But the ith guy, I don't know what the ith guy is. I'm trying to find the ith guy, but my claim is that if I calculate d primes and then for the ith guy, d prime is the real distance. Why is it the real distance with the ith guy? Because the ith guy doesn't need anybody other than the first I minus 1 guys, right? Yeah? Remember, we want to find vertices in increasing order of distance to the source, right? The ith guy doesn't need anybody else other than the first I minus 1 guys. So we actually found its right distance, whoever it is, right? For that guy, we know the distance is right. Okay? D prime SU is exactly distance SU. Okay? And he is the smallest among all the d prime values. So he must be the right guy. Okay? That's the principle of Dijkstra's algorithm. Okay? We are finding vertices in increasing order of distance from the source. Okay? Alright, that's the correctness proof, but the algorithm is very simple, right? What is the algorithm? You just have to keep on updating this d prime value and at each step take the minimum guy. Okay? So the algorithm is very simple. It is, I wrote it slightly differently. For each vertex, we initialize the distance to infinity, right? We are maintaining these d prime values. And initially, X is empty set, and we know the distance from d prime S to S is 0, right? So for I equal to 1 to the number of vertices, we pull out the guy with the smallest d prime value, right? I change the loop a little bit. We pull out the one with the smallest d prime value. In the beginning, it will be the source, and we know that that's the right guy, right? You know, this one with the smallest d prime value is the next guy that we'll discover, okay? And once we pull that guy into the set X, we need to update this d prime value, right? Why do we need to update the d prime value? Because the set has increased now, right? We have I guys in the set instead of I minus 1 guys. Okay, how do we update the d prime value? We want to do it a little cleverly, right? We don't want to recalculate everything, right? So in terms of the example, okay, let's see this example, right? What is the d prime value we have for d right now? It is 6 plus 30 or 13 plus 20, right? So we have what? 33, right? Yeah? So right now this guy's d prime value is what? 19, right? And what is this guy's d prime value? 38, right? Yeah? Is that clear? Okay, now who is the smallest? We find F is the smallest guy, so he is the next guy in our list, right? Okay, but what happens to this? Once we add this guy, what happens to the d prime value for this? It goes down, right? Okay, how do we update the d prime values for once we add one more vertex? What should we do? For everybody, we can do the recalculate the thing, right? But instead, we could save some work by saying, look, the only reason the d prime value for this would change in the next iteration is because this guy became part of the set X, right? Okay, so we don't have to recalculate 13 plus 20 and again, right? We simply say, oh, F became part of the set X, so let's scan all the edges out of F and update all the vertices that this is adjacent to. Yeah? That makes sense? Right? Instead of recalculating the d prime value because X has increased by 1, we can do that by keeping track of the old d prime value and only updating the vertices who are adjacent to the new guy that came to X. Yeah? So that's what we do, right? You know, when this guy became 19, became part of the thing, we say, aha, the value of this now should be minimum of 33 and 19 plus 6. Yeah? So the amount of work we do when we add a vertex is proportional to what? The edges out of that guy, right, we added. Yeah? When a new guy gets added, we scan its edges and update the d prime value of all the guys that are adjacent to it. That's the only work we need to do, no? Is that clear? Okay? So that's just an implementation issue. Yeah? We are being a little bit more clever. Instead of saying, recalculating every d prime value, we update the d prime value. And so that is the algorithm basically, right? That is Dijkstra's algorithm, right? Dijkstra's algorithm is very simple, but you have to think about why it's correct, right? We remove the guy with the minimum d prime value. We know it's the right distance now. It's the correct distance. And for everybody who is adjacent to that, we update. Okay, this guy is still inefficient, so let me, okay. Okay, this is going, this is okay. So once you pull the new guy into the list X, you update the d prime values by just looking at the old value and the new distance you might get by going through the new vertex. Yeah? Okay, that's the only difference. Yeah? Okay, is the algorithm clear? Initialize X to empty, distance from S to S is 0. We forget about d prime now. It's just one number. 1 to V, pull out the vertex with the minimum distance value among all the guys who are not already in X. That guy becomes part of X. For each of the vertices which are adjacent to that new guy, update the distance value. Is that clear? Yeah? We are doing the same algorithm. Yeah. No, not O of one time. It depends on the number of edges incident to the vertex, right? Okay. So what is the running time of this algorithm? Let's calculate the running time of this algorithm. Yeah. Hey, this is just a lookup. This one. This is just a lookup. Yeah, that's an edge length. Yeah, right. Okay. So what are how much work will this do? How many iterations do we have? N iterations, right? One per vertex. We are discovering one new vertex at a time. What is the work we are doing? We are maintaining some distance values, right? Okay. So we have to find the one with the smallest distance value. Okay, how should we do that? Okay, you could either use a data structure, and let's not use data structure. Let's be silly, right? We store a bunch of numbers, right? And we go through the numbers and find the one with the smallest value. Yeah? Okay, that's fine. How much time will that take? If I have a list of n vertices, finding the minimum by just scanning the array takes n time, right? Yeah? Okay, can you do this in n time? Okay, good. What about this update? It depends on how much work am I doing, the out degree of the vertex I have, right? Yeah. So over all iterations, how much time will I spend on this? N times n, right? Yeah, that's n square. But how much time will I spend over all iterations for this step? Okay. It's basically, if I do this, the total work I spend here is only linear in the number of edges, right? Because every vertex goes into the set only once, and I scan it once, right? So the total work for all these iterations is just linear in the number of edges, and this takes n square, right? Yeah? So the running time is what? N square plus m. Yeah? Is that clear? Yeah? M is the number of edges. M is always the number of edges in a graph. If you don't have say anything else, n is the number of vertices, m is the number of edges, okay? So this work over all iterations is what? Once I pull a vertex in, I scan its edges. That's it, right? So the total work I do for this is the sum of the out degrees of all the edges, which is at most n, right? And this takes n time, right? So should we do it by scanning an array? We should not do that, right? What data structure would you use here? It's a priority queue of some kind, right? Okay, but you don't even have to think of the priority queue. What do I have? I have a list of numbers that I'm keeping track of, and I want to find the minimum, right? All right? And I also need to update them as I go along, right? So the priority queue is the right one, right? And you can do that, and that's what we'll do, right? So, so everybody knows what a priority queue is. I'm assuming you do that, but you know that. But let's just go over the operations that a priority queue has, right? What does priority queue allow you to do? It allows you to keep track of some kind of numbers, right, with keys. And what are the operations that you need? You have to initialize a priority queue. You want to find the minimum number in the priority queue, yeah? You want to take it out. You want to find sometimes the minimum, and you also want to take it out, right? You want to insert a new guy, right? And you want to delete a guy, right? These are the operations you want in a priority queue, yeah? Okay, and these are things that you normally don't see in a priority queue. And in fact, Dijkstra's algorithm was the reason why people thought about these operations. This is called decrease key. What is decrease key? You want to take a guy in the priority queue and reduce its value. Yeah? Only reduce, not increase. Okay? Reduce. Okay? And there's another operation called meld, which again is not so standard or not so common, that you want to take two priority queues and make them into one priority queue. Okay? Don't worry about that, but this is important. Okay? All right? Okay, now let's rewrite Dijkstra's algorithm using this data structure because we want to speed it up a little bit, right? Okay, and you know standard priority queues. How long does extract min, find min, insert and delete take if you use heaps? If you have n keys, you take log n time to do that, right? You don't even need to use heaps. You can use binary search trees, no? You can just take the minimum guy, right? Heaps are just one way of doing it, right? Okay, so let's rewrite Dijkstra's algorithm using priority queue, right? Remember, this is just speeding up the algorithm, not thinking really about correctness at this point, right? We are speeding up the algorithm. So it's so simple, right? So what do? You start with an empty queue, yeah? And you initialize, you insert into the queue s with what? Value what? 0, because we know the distance to s. For each node which is not the source, you insert it with what? Infinity. Right? Initially, we don't have any estimate to the vertex, right? Okay. And then x is empty. What is x? The set of vertices that we've already found the distance to, right? For I equal to 1 to n, you pull out the guy from the priority queue with the smallest value of the key, right? Yeah? Okay, you do that. That's extract min. And x becomes one more, the new guy. Now, what do? You scan the edges out of the new guy, right? But what do you do when you scan the edges of the new guy, right? You update the distances, no? Can the distance go up or go down? Only go down, no? Okay, so that's what we're saying. We are going to decrease we're only going to do decrease key, right? Okay, so we look at the guy who is adjacent to V and we update it to the new value, yeah? Okay. So, see, look at how simple the code is if you use data structures, no? Yeah, okay. So, okay, now let's count the operations we are doing in this data structures. What do you do here? You start the queue. How many insertions do you do? N insertions in the beginning, right? How many times do you extract the minimum guy? N times, right? Each time you write, okay. How many times do you do decrease key? The number of edges, right? Because each time you add a new guy to X, you scan that guy and you will do how many decrease key operations? All the edges incident to that guy, right? So over all the entire algorithm, we scan all the edges once and we will do that many decrease key operations, right? So M decrease key operation, okay? How can you implement, if you didn't know decrease key, how would you implement decrease key in a priority queue? Not extract, delete and insert, no? See, if I want to update the distance in a priority queue, what should I do? I have to take it out and put it back in, right? Yeah? That's really what I can do, right? Yeah? Agreed? Okay. So, I can implement decrease key using deletion and reinsertion, no? Yeah? So, if I did that, how many times will I have? What are the number of operations I get? M plus N insertions and deletions, right? And N extract means. What is the total running time of the algorithm if you did that? Log n for each operation. So the total number of operations is m plus n. So we're doing m plus n log n. Yeah, m plus n times log n. That's it. Dijkstra's algorithm takes m plus n log n. If you did, just basic thing, right? Okay. Agreed? Simple enough, no? Okay. That's Dijkstra's algorithm, right? Dijkstra's algorithm can be implemented in m plus n log n time. Yeah. Okay. Now the only question is, can we make it faster? And I just want to tell you, even though we're not going to do this, you can implement decrease key in constant time. Okay. How? Very complicated. Okay. It's advanced data structure, right? So decrease key was motivated by Dijkstra's algorithm. People didn't think of decrease key before. They didn't think it was useful till they saw Dijkstra's algorithm and said, wait a second, can I do decrease key better? Okay. Okay. What is amortized time? Amortized time means that over all operations it takes constant on average. Okay. Don't worry about that. Okay. Okay. So, but now assuming that you had this fancy data structure, then the running time becomes n log n plus m, right? Why? Because the number of operations we are doing of decrease key is m, extract min is n, and insert is n, right? Okay. So if I gave this as constant and this is log n, what do you get? M plus n log n. Is that okay? So I'm not telling you how to do decrease key, but if you do that, then you will get m plus n log n. Okay. Why is this good? Why is this good? If the graph is dense, we removed a log n from m, right? Instead of m plus n times log n, we are getting n log n plus m. Yeah? Yeah? That's good, no? Good or bad? So that's the reason to do it, right? So that is Dijkstra's algorithm, right? Agreed? Any question on Dijkstra's algorithm? Some people think of Dijkstra's algorithm as a greedy algorithm. Don't think of Dijkstra's algorithm as a greedy algorithm. Okay? Think of Dijkstra's algorithm as adaptation of BFS when the edge lengths are arbitrary, right? It's a simulation of BFS on this implicit graph. Okay? It's not a greedy algorithm. By no means is it a greedy algorithm. Okay? It is a very well understood, clear principle of why it's working. Yeah? Well, that's because of if you use a fancy data structure called Fibonacci heap or other things, the decrease key operation takes only constant time. And we're only doing m decrease keys and n extract mins, right? And n insertions. So decrease key is the more number, we're doing m of those operations and n of extract mins. So if I make the decrease key operation constant, then you will, okay? That's the, okay. As you know, Dijkstra's algorithm is also at the same time is discovering a shortest path tree. Okay. Just as BFS discovers a tree, Dijkstra's algorithm will also create a tree for you. Okay. How do you create the tree? What edges are creating this tree? So what is going on is, so here is what is going on, right? So when we start with 0, when we discover a new vertex, we add a link to the guy to who? Okay, this guy added a link to 0, that guy will add a link to 0 because when you add this guy to the set, why did you add him to the set? Because you found the shortest path to that guy through somebody, no? What is its d prime value? Its d prime is defined by the shortest path using only these two vertices, right? And without loss of generality, it's uniquely determined, right? Maybe ties are there, right? So when we add this guy, so why did we add an edge from 19 to 9? Because we found the shortest path to this guy through 9. So whenever when we add the next guy, we keep track of how did we find the distance and add a pointer, right? That will create a tree for you. Okay. So what is nice thing about shortest path tree is that it's a compact representation of the shortest path distances from the source to everybody, right? That's nice. It's not obvious that there should be one such, but you get that as a bonus because it's a nice thing, right? Okay. So that is easy to compute along with Dijkstra's algorithm. That is easy to see. Okay. So this is a simple question. Dijkstra's algorithm allows you to find the shortest path from S to everybody, right? What if I want shortest path distances to S? The trick should be clear by now, right? You reverse the graph, no? Yeah? You want to find shortest path distance to S from everybody, you can reverse the graph and do Dijkstra's algorithm, right? Agreed? Okay, all right. So, okay. So in undirected graphs, you don't have to do the reversal because it's the same graph, right? So you don't have to worry about that. Okay, here is another problem. Suppose we are given two sets of nodes, right? S and capital S and capital T, which are disjoint. I want to find the shortest path from capital S to capital T. What does that mean? Among all guys in S and all guys in T, find the pair which has the shortest distance. Okay? Is this well defined? Right? Okay, think of it like this. What is, let's think of, so that there's, I want to find in this, right, the shortest path from these students to that row students, right? Right? Which one it is, right? It could be any pair, right? How do I find that efficiently? Yeah? Is it clear what I'm asking, right? How do you do that? Yeah, so you have to remember these tricks, right? You add a new vertex, okay, and find the shortest path from this new vertex to this new vertex. Okay? Yeah? That gives you what you want, right? Yeah, you don't want to do the naive thing of finding for every pair the shortest path distance and then computing the minimum, right? This will give you one shot. Yeah? So these graph transformation tricks are very important. Okay. Here is a toy problem to solve, right? So, I mean, suppose you want to go, you're going to a party, right? All right? Your friend is somewhere on the map, and you want to stop and get some, I don't know, beer maybe, or dessert, whatever you want to buy, and you want to find the shortest way to do that. Okay? So what is the input to the problem? The input to the problem is a graph which represents distances, right? Your source is you, where you are right now. Your destination is your friend's place, and you want to stop at a store, right, to get something, right? So there are many possibilities of the stores, right? Maybe you want to go to, a subset of the nodes are where the stores are. So you want to go from your place to your friend's place with a stop in the middle at one of these locations, right? Because you want to do it in the shortest possible time. What would you do? How do you compute that? Yeah? Yeah, so how long will that algorithm take? There are many stores, no? There may not one. If it's one store, it's obvious, no? Suppose there's only one store you want to go to, right? Sure, you go from S to that store to, right? But there are now 100 stores, right? Okay, what is the naive algorithm? Yeah? What does it mean to be a store on the way? Maybe there is no store on the way, right? Okay. No, but I want you to see, the first goal should be to find the correct algorithm, not the fastest algorithm. Okay. So you want to make sure that you find the store with the smallest distance that you travel, right? That's higher priority than finding a fast algorithm. Yeah. Yeah, that's at least conceptually it is, you are not worried about correctness, right? Because if you try every store, right, that's a polynomial time algorithm, right? This store, if I have to go to this store, what is the distance? I can do that, right? I can go from S to that store to T, and do this for every store and take the minimum. That you're happy because that's a definition more or less, right? Okay? Agreed? So how long will this take is the only question, right? It'll take, the number of stores times 2 shortest path computations, right? Okay? Okay, but you are dead certain that this will work because it is the definition, right? But you have to be careful. That's what you need to first think about, right? Aha, that's correct, right? Now you want to speed it up, okay? Can I speed up this computation? What does Dijkstra's algorithm give you? It not only gives you the distance to one guy, but it gives the distance to everybody, right? So if I did Dijkstra's algorithm from the source, what do I get? I get the distance to every store in one shot, no? I don't have to recalculate that, yeah? Right? Okay, I can do the same thing, right? I can compute distances from everybody to the destination, yeah? Because Dijkstra's algorithm will give you that too, right? If you do the reverse of the graph from the destination, I can get from everybody to the destination all the shortest path distance. So I already have all the information for this brute force algorithm, but I'm only doing 2 Dijkstra's computation, no? Is it clear? Right? So now I have all this number stored, I just do the same loop. For every store, compute the distance from S to that, and from that to T, and add them up and take the minimum, right? But I'm not doing the Dijkstra's again and again because I did the Dijkstra's once from S and I found all of them and stored them. I do Dijkstra's from T, I store them, and I just do one loop of taking the minimum. Is it clear? Okay, so that's important to remember, that Dijkstra's algorithm gives you the distance from S to everybody and not just to the destination. Okay, all right? And you have it stored in a shortest path tree. It's a very nice compact data structure. Okay, that is a small trick question, right? It's actually a very easy question in a certain sense, but just noticing that Dijkstra's algorithm gives you. So what I want to emphasize is that when you see a problem like this, your first goal should be, am I getting the right answer? Not the fastest algorithm, okay? That will lead you astray if you try to emphasize the speed before you actually understand the structure of the problem, okay? That's important to keep in mind, all right? Okay? So that's what I want to tell you about Dijkstra's algorithm. I think you've seen it before, but I hope the point of Dijkstra's algorithm is not so much to reteach it, is not so much as much as to make sure that you understand the properties that underlie the development of the algorithm, right? And then how to use shortest path computations to solve some simple variations rather than the most basic one. Okay, so now we understand, yeah, you reverse the graph, yeah. I mean, you can also implement implicitly if you want, right, by looking at incoming edges instead of outgoing edges. But conceptually, it's better to reverse the graph and do it, right? Okay, now this graph is interesting, right? It has negative length edges. Okay, can I see? There are some negative length edges, right? Okay, and now I ask you to solve the shortest path problem with a graph where the edges can be negative length, then what happens? Right, so what would your first instinct be? Yeah. Yeah, thank you. Because I was going to, that's a natural instinct, no? Let's add a big number to everybody, right? And make everything look positive and then find the shortest path in that graph and, okay. Why does it not work? Okay, I mean, what he said is, recasting it, shift everybody's edge to be positive by adding a big number. Okay, what goes wrong? So, but first, you have to see, instead of me saying what goes wrong, whenever we come up with an idea, we have to say, why is it correct? Right? Yeah. Yeah. Is bigger for the right. So I can have two different paths from S to T. One has 2 edges, one has 3 edges, say. If I add a shift, the guy with more number of edges is getting harmed more, no? Even though that's not what you intended. Yeah? Okay? Right? You're not guaranteed that different paths have the same number of edges, right? But if you add a big number to it, the paths which have more edges are getting harmed a lot, right? Even though their total length might be small. Okay, you can easily construct examples where it won't work. Because it's nothing about non-negativity, right? You can try the trick even for positive edge lengths, right? What if I change all edge lengths by adding a 10 to everybody, right? Something goes wrong and this is what goes wrong, right? So same reason it won't work. The other thing is, maybe you think Dijkstra's algorithm will still work. Yeah? So wait a second, why not? I have a Dijkstra's algorithm, why don't I run it? Right? Now the second thing we can ask is Dijkstra's algorithm correct? Okay, so let's see. What is the shortest path distance from S to W in this graph? Simple graph. Right? One, right? If you go this way, the length is what? 5 minus 5 plus 1, right? If you go this, there are only 2 paths from S to T, S to W. This way it is 3, right? What do you think Dijkstra's algorithm will do? So it'll start by saying, oh, okay, it'll find who's the first guy it'll add? Y, right? Okay, and then it'll add Z, right? Yeah? Agreed? And then who will it add? It'll add W. And then it'll add X. Okay? Then you may say, when it is scanning X, it'll realize, something went wrong maybe, right? If you actually check carefully, if the code checks carefully, it may realize, wait a second, something is odd here, right? But if your code doesn't check and it thinks it's okay, then you will stop, right? Depends on how you implement the algorithm, right? Okay? So something did go wrong in Dijkstra's algorithm, right? Okay, normally you would stop here and say done, right? My loop finished, right? So clearly something went wrong. Okay? Okay, so what went wrong, right? Why doesn't Dijkstra's algorithm work when there are negative length edges, right? This teaches us about why Dijkstra's algorithm works in the first place, right? What assumptions were used in the development of Dijkstra's algorithm. Okay, so that's clearly wrong, and the false assumption is, what was the principle behind the development of Dijkstra's algorithm? The principle is the following, right? If I have a shortest path from S to a vertex Vk, we know that for everybody in the middle, this is also a shortest path, okay? That is true whether the lengths are negative or non-negative. But it is not true that the length of the path here for the middle guy is actually shorter than the length to the last guy, right? So, you see, look at the length from S to W. Is that a shortest path? Yeah? What is the distance from S to W along this path? Is 1, right? Okay. So what is the distance of the guy to X in the middle? 5, right? What went wrong? The guy in the middle has a distance which is bigger than the guy at the end, right? Okay. So I cannot discover vertices in increasing order of distance I may have people on my path who have a longer distance than my distance because of negative length edges. Yeah? So Dijkstra's algorithm is predicated on discovering vertices in increasing order of distance from the source. But that means that I have to discover W before X, which is not possible because W is not connected even to S, right, directly, right? So that's the reason why Dijkstra's algorithm fails. Okay? You can't discover vertices in increasing order of distance. Okay? So we need to do something else. But there's another problem with negative length edges. Look at this graph. I ask you, what is the shortest path from S to T? Okay? It's hard to see, no? Okay, because it's a complicated. Okay, but look at this. There is something going on here. Look at this red cycle. What is the length of the cycle? Minus 16, 11, plus, so minus, okay. So what is the length of the shortest path from S to T? I don't know, right? So are we allowed to go around? But is that a path? No, right? Okay. So now, we didn't think about this distinction when the edge lengths are non-negative, because even if I allow you to run around, it can only increase the path length if the lengths are non-negative. Okay? So the length of the shortest walk from S to T is no more than the length of the shortest path, right? Or they're exactly the same when the distances are non-negative, right? But if I'm allowing you negative length edges, a walk may allow you to reduce the distance, right? Okay? Okay, so now we have a trouble here, right? The length of a shortest walk is different from the length of a shortest path, right? Because path is not allowed to visit. Okay, now what do you want is the question, right? It depends on the application, right? Maybe you want to find the length of a shortest walk, but maybe you want to find only the length of the shortest path, right? Both are interesting depending on your application. Okay. So if there is a negative length cycle, then the length of the shortest walk is what? Minus infinity, right? Because if I have this, what is the length of the shortest walk from S to T? Because I can go around this cycle again and again and again and again, and its length is negative, I can make it as small as I want, right? So I should technically define it as negative infinity, right? Okay. But maybe that's not what you want, and you say, I only want the length of the shortest path. I don't allow you to go around. It's a path, it's not a walk, right? Okay. So you can ask for both problems. Can we solve both of them? And it turns out that finding the shortest path is actually NP complete. That is, if there are negative length edges, finding the shortest path is actually NP complete. Why? Because if you can solve the shortest path with negative lengths, I can find the longest path with positive lengths, right? So I can negate the edges and find the longest path. Okay? And that turns out to be a hard problem. So even though you may be interested in finding the shortest path, you can't solve it. Or at least we don't know how to solve it. You'll be very rich if you can solve it, right? Okay, so but we can solve this problem, which is length of the shortest walk. Okay, so implicit in that problem is the following thing. So we are not going to be able to solve the shortest path problem. So we are going to focus on this problem. I give you a graph. The lengths can be non-negative, negative. I give you S and T. If there is no negative, if there is a negative length cycle, you have to tell me there is a negative length cycle. Because in that case, what do I know if there is a negative length cycle? I could get minus infinity, right? Then I mean, there's some small technicality there. If there is a negative length cycle, you have to tell me there is a negative length cycle. If there is no negative length cycle, the shortest walk and the shortest path are the same, right? Because if you have no negative length cycle, you cannot reduce it again and again, right? So in that case, you have to give me the right shortest path distance, okay? And that's what you need to solve, right? Either tell me that there is a negative length cycle or find me the shortest path distance, okay? And we'll see that we can't use Dijkstra's algorithm, so we have to do something else. Yeah.
If we use stress algorithm, can we frame the runtime to be an organ task? I'm using the